Assalamu alaikum. Today we'll talk about Chapter 8 Electromagnetism and Electromagnetic Waves. At the beginning, we'll talk about magnetism. As we know, the Chinese people are the first people who discover the magnetism. They found that a piece of stones attract other pieces of iron, and these stones orient itself north and south if suspended by a thread. Now we have different size of magnets and shapes, but all of them have something in common. All of them, they have a north pole as we see here, and south pole. Also, if we have a magnet and if we broke it into two pieces, each part will have its own north pole and south pole. What's that mean? This means here, as written, no way to get single magnetic monopole. It's different than electricity. We can have a single charge, positive or negative charge, but in magnetism, no way to have a single magnetic monopole. Other features, as we know, like electricity, balls repel each other, as we see here, north. This is north with north. This is repulsive force. And unlike balls like south and north attract each other, it's exactly like electricity. If we have positive charge, we have repulsive force, and if we have negative, we have attractive force. Okay, here we will classify the material according to its magnetism to three materials. The first one called the ferromagnetic material, and the second one the paramagnetic material, and the third one the diamagnetic material. Here in this chapter we'll talk only about a ferromagnetic material. The ferromagnetic material is exactly like iron or metals in general. What's that mean? The ferromagnetic material, are material in which the magnetic field is induced when it's near a magnet. What's that mean? Suppose we have a magnet like this. This is north and this is south, and we brought a ferromagnetic material like metal. What happened to this material? This material will be attracted, or the magnet will attract this material. Why? Because a magnetic field induced inside this material, and here will appear the south pole, and this is called north pole. That's why this magnet attracts this ferromagnetic material like iron or other thing. Once we remove this magnet, what happened to this material? It returns back to itself. It will not keep its magnetism. However, other material can maintain the magnetic field induced inside them. Such material are called permanent magnets. Now we'll talk about the magnetic field, as we talked before about the gravitational field and electric field. The magnetic field in general is the area around the magnet that can act a force on any magnetic material that lies very close to that area. How we represent or how we map the magnetic field lines? The magnetic field lines are imaginary lines, and these lines, the magnetic field lines goes from the North Pole toward the South Pole outside the magnet. However, inside the magnet, it goes from the South to North Pole. How we represent or how we map this magnetic field line? We can use a compass needle and locate it in any place. So the compass needle will orient itself to the direction of the magnetic field. You can put it here and you can put it here, so it will orient itself in a different direction, which is in the same as magnetic field line. Now we will talk about the Earth magnetic field. The Earth is considered a huge magnet. Here in this picture first we will talk about this is the axis of rotation of the Earth here, and this is the North geographic pole in this picture, and here this area the South geographic pole. Here we represent the magnetic Earth is as a huge magnet lies here, and this is the magnetic axis. As we see, the magnetic axis tilted almost 11 degrees from the axis of rotation. What happened? Yeah, this represent the south magnetic Earth, and this is represent the north magnetic field. So what happened if we placed a compass needle here? It will orient itself with the magnetic, the Earth magnetic field, but this here it will point it. It will be the north pole, which will be in the same direction as the south magnetic pole, and this is the south pole, which will be in the same direction as the north magnetic pole. Yes, as we mentioned before, the geographic North Pole corresponding to the magnetic South Pole and vice versa. Also, the North Pole of the compass needle points to the geographic North Pole because it's the magnetic South Pole. Yeah, here regarding the poles of the magnet, the Earth magnetic poles are not stationary. The South magnetic pole is not exactly where it was 20 years ago. These poles can swap every 100,000 years. Now we will summarize the key aspects of electrostatics and magnetism, or we can say I will talk about similarities and differences between magnetism and electrostatics. The similarities between magnetism and electrostatics, first thing, we have two poles, North Pole and South Pole. Also, we have two kinds of charge, positive and negative charge. This is the first one. The second one, we know like poles repel each other, and we know like charges repel each other. The third one, we know there is a magnetic field around any magnet, and also we have an electric field around any charge. The differences, regarding the differences, we know each kind of charge can exist separately. We can have a single positive charge or a single negative charge. However, no way we can have a single magnetic monopole. Always the magnetic poles come in pairs. Here we will talk about electromagnetic, which is the science that studies the interaction between electricity and magnetism. And we know in our daily life there is a lot of machines use electromagnetic properties, such as electric motors, vacuum cleaners, computers, microphones, microwave ovens, and many other. Now we'll talk about the three basic observations which come from the interactions between electricity and magnetism. The first one, only a moving electric charge produces a magnetic field in space around it. Here we have a charge, and this charge is moving, so it will produce a magnetic field which look like a circles around it. Also, the current, which is a flow of charge, produces a magnetic field around it. As we see here, this is the current and this is the magnetic field line, which look like a circles around it. So what happened if we reverse the current direction or the movement of charge, like here? Suppose we have this current like this, so we will have a magnetic field. This is I current, so this is the magnetic field line will be like this. So it will we change the magnetic field. How we know the direction of the magnetic field? We can use the right-hand rule, which says that the magnetic field lines produced by a current carrying wire will be oriented in the same direction as the curved fingers of a person's right hand, with the thumb pointing in the direction of the current flow. As we see here, the forefinger pointed to the direction of the magnetic field, and the current represent the thumb. As we mentioned in the previous slide, that the DC or direct current produces a magnetic field around it, and this magnetic field depends on the amount of current through the wire. So if we have two wires, 5 ampere and 10 ampere, so the 10 ampere wire will produce a stronger magnetic field than 5 ampere wire. Also, the strength of magnetic field depends or inversely proportional to the distance from the wire. Suppose we have here this wire, and we have this point. This is the magnetic field at this point A, and we have another point at B. So the magnetic field strength at B will be less than the magnetic field at point A. Most applications and machine uses a coil instead of a straight wire. So what's the coil? The coil is a wire, but this wire is wrapped in the shape of cylinder, and usually it has an iron core. We use an iron core because it's ferromagnetic material, and the magnetism induced in the iron enhances the magnetic field of the coil. Here, look at this figure. Once the current passes through this wire or this coil, it will produce a magnetic field. We have here north pole and we have here south pole. Look at this, the shape of the magnetic field. It looks exactly like the magnetic field line produces from the bar magnet. However, what happens if we reverse the direction of the magnetic field? The same thing, we will have change in the direction of magnetic field. We will have here the south pole and we will have here the north pole. So we see here that the magnetic field produced from the coil behaves like a permanent magnet, but only while the current is flowing. And this is considered advantage of using a coil to produce a magnetic field over using a permanent magnet, since once the current is stopped, the magnetic field vanishes. Now we will talk about different type of coil called solenoid, which is a coil with a length much larger than its diameter. So what happened when we brought this iron rod to this circuit? So once the current passed through the circuit, here we have the current will pass through this coil, so it will produces a magnetic field. This is the north pole and this is the south pole. So this is, we have the shape of the magnetic field from the north to south. So what happened if we brought this ferromagnetic material very close to this magnet now? It will induce a magnetic field inside this rod or the iron rod. So here we'll have south pole and we have north pole. That's why we will have north-south. It will be attractive force, and so the force or the magnetic field that produces from this circuit will pull the iron rod inside the magnet. This figure shows us the solenoid and how it's found in most of the machine, like non-digital doorbell chimes, electric door locks, starter motors on car and truck engines. Here we want to see the differences between non-ferromagnetic materials and ferromagnetic material in the presence of an external magnetic field. For non-ferromagnetic materials, suppose we have this microscopic cross-section, we see that the electron here The electromagnet fields are randomly distributed and cancel each other, so the net magnetic field produced from it equal 0. However, for ferromagnetic material, the external magnetic field forces the electron to align in such way that can induce a magnetic field. The second observations which come from the interaction between electricity and magnetism is a magnetic field exerts a force on a moving electric charge, or we can say the magnetic field exerts a force on a current carrying a wire. Here I just want to remind you of the first observation. We say a moving electric charge produces a magnetic field. However, here a stationary electric charge will not produce a magnetic field, so it will not experience any force if we place it inside a magnetic field. The second observation is in line with the first one, which means that anything that produces a magnetic field will itself be affected by other magnetic field. Suppose we have here this coil and there is a current passes through this coil. Suppose this is the current like this. So this will produce a north pole here, and this is south pole. So if we place it inside another magnetic field like this, north, south, what happened? This coil will experience a repulsive force, or there will be a repulsive force between the two magnets. Here we want to mention that the direction of the magnetic field produced by a current carrying wire is perpendicular to the direction the current is flowing. Also, the force experienced by a moving electric charge in a magnetic field is perpendicular to the direction of the magnetic field and current. I will explain the previous slides. The first statement, which was the direction of the magnetic field produced by a current is perpendicular to the direction of the current, as like this. This is, suppose we have this current, and this will produce a magnetic field which is like circles around it. So the direction between the magnetic field and the current is 90 degrees. It's always perpendicular. The second statement, which talk about the force that experienced by a moving electric charge inside the magnetic field, which will be always perpendicular to the direction of the field and the current. Suppose we have this magnetic field lines pointed to y direction, and there is a current here pointed to x direction. This is the current. So the current will experience a force, and this force will be perpendicular to both x and y, to the magnetic field and the direction of the current. It will be where? In the z direction. This is the force here. Z direction. This is the force perpendicular to both x and y. In this figure we have a magnetic field, and this is the magnetic field lines goes from the north to south. Suppose we place a current carrying wire inside the magnetic field like this one. So this current or this wire will experience a force from the magnetic field. It will be up. So this force will be perpendicular to both the direction of the current and the direction of the magnetic field. Suppose the direction of the current is x and the direction of the magnetic field y. So the force will be in z direction, which is perpendicular to both x and y. Suppose we reverse the current. What happened to the magnetic, the force that experienced by this current? It will be changed to the opposite direction. The electric motor is considered an example which exploits the electromagnetic interaction. Here in this graph we have a magnetic field. Suppose we place a coil inside the magnetic field. Once the current passes through this coil, this side will experience a force, and the other side will experience the same force but in the opposite direction. And since the two forces are not in line, so this coil will start rotate. Here, if we want to keep the coil continue rotating, we have to reverse the current each time the loop becomes horizontal. Now we'll talk about the third observation, which comes from the interaction of electricity and magnetism, which is considered the basis of electric generator. Before I will talk about this, I'll just remind you with the first observation. We mentioned that a moving electric charge producing a magnetic field around it. So we produces a magnetic field from a moving charge. So the scientists start asking themselves why we can't produce an electric field from the moving magnetic field. So this is the third observation. A moving magnetic produce an electric field in space around it, which is considered the process is known as electromagnetic induction. To explain the third observation, suppose we have here a coil and this coil is connected with a meter. Here we don't have any battery, so there is no current this time, and we have a magnet. Suppose we move the magnet to the left, we will see a current here. And once we move it to the right, we will see the current, but in the different direction. And once the magnet is stopped, no current. So a moving current, this is the third observation, a moving current, a moving magnet produces a current in a coil. This is the generator, which is considered the basis of the third observation. Here we have a coil, and this coil inside a magnetic field. Once this coil starts to rotate inside this magnetic field, a current will be produced through this coil. From the previous slides, we can make two general statements about electromagnetism. The first one, an electric current or a changing electric field induces a magnetic field. This means we can produce a magnetic field from a moving charged particle. The second one, a changing magnetic field induces an electric field. We can produce an electric field from a moving magnetic field. One of the applications of electromagnetism is the transformer. The transformer is a device which used to transform the voltage from high to low or from low to high, and it uses here AC current. Also, I want to remind you in the previous chapter about AC current and DC current. DC current is called direct current, and AC current is called alternating current, which is the current is time varying current. And regarding the first observation, we know that the current produces a magnetic field around it. So if we have a DC current, this will produce a steady magnetic field around it. And if we have an AC current, this will produce a time varying magnetic field, which means this will be a change in a magnetic field. Here is the transformer. The transformer consists of two coils. This is the first one, the input coil, and this input coil is connected with the AC current, and the second one is the output coil here, and here there is no current passes through this coil. Once the AC current passes through this coil, this will create a change in a magnetic field. So now the output coil will be lies in a change magnetic field, like you having a magnet and a coil, and once you start moving the magnet back and forth, what will happen in the coil? There will be a current. So since this output coil lies in a change magnetic field, so the current will produce in the output coil. Here, why does not a transformer work with DC current? We know that the DC current produces a steady magnetic field, and we need changing magnetic field to induce electric field or current in the output coil. In the transformer, we know that we have input coil and we have output coil. So for the ideal case, the power input should be equal to the power output. And we know from the previous chapter that the power equals the multiplication of the current multiplied by the voltage. Once each loop of the coil has the same voltage induced in it, we can find the total voltage by adding the voltage of each loop, because each loop or all the loops are connected in series, and we know in the voltage in series we add it together. As we know, the transformer used to transform the voltage from high to low or from low to high. And this can be done by playing with the number of turns or the number of loops in the output coil or the input coil. This equation relate the voltage the output voltage and the input voltage with the number of turns in the output coil and the number of turns in the input coil. So in the step-up transformer, we need to increase the output voltage. So what we have to do, we have to increase the number of turns in the output coil. In out should be greater than in I. Also, in the step-down transformer, we want to decrease the output voltage, so we have to decrease the number of turns in the output coil. In out should be less than the number of turns in the input coil. Here is an example. A transformer is being designed to have 600 volt output. So we have the V out 600 with a 120 volt input. So Vn 120 volt. If there are 800 turns of the wire in the input coil, so this is Ni, number of turns in the input coil, how many turns must be there in the output coil? So before we start solving these questions, what's this type of transformer? Is it a step up or step down? Since we are moving from 120, the input coil, to 600 volt, the output coil, this is step up transformer. So we expect the answer, the number of turns, to be more than 800. So if we want to move from low to high, we have to increase the number of turns. Look at the answer here. This is, as we mentioned, V out 600 and V in the voltage 120. This is the number of turns in the input coil 800. Just we use the equation direct and we can find the number of turns in the output. So the number of turns will be 4,000 since it's step up transformer.